Hello, this is Yongfei, Wang from Southern California Earthquake Center at the University of Southern California. Today, I'm going to present how to use physics-based simulation to quantitatively address the fault displacement hazard. However, for some shallow and large enough earthquakes that have substructures, the seismic hazard can be directly caused by the ground breaking instead of shaking. Substructure makes prominent ground deformation and then damages the civil infrastructure over and near the fault trees. Here are two examples of fault displacement hazard. In the left panel of 1999 Chichi earthquake, the waterfall in the river channel resulted from about 6 meters of fault offset in the bedrock. The fault cut across the bridge caused the collapse of the decks. In the right side, the 2019 Ridgecrest earthquake particularly damaged the lifelines. In here, water and gas pipes. Displacement demands used in engineered design are usually defined by using probabilistic fault displacement hazard analysis (PFDA) that is based on the empirical fault displacement dataset. Compared to ground motion dataset in GUS2, the PFDA models are sparse and poorly constrained, partially due to the scarcity of detailed fault displacement observations. It is because the only relatively large earthquake have substructure. Number two, long recurrence period between the two substructure events. Number three, technical difficulty in collecting detailed perishable fault displacement. Overall, this data shortage may hinder the PFDA model development. Fortunately, a physics-based dynamic rupture model can help to resolve this issue because the dynamic model imposes physical parameters like stress, friction, fault geometry to constrain a physically plausible simulated fault displacement profile. In this study, our goals are quantifying the fault displacement generated by a physics-based model and supplementing the empirical dataset with the simulated fault displacement datasets. But for viable extrapolation of models, simulation must first be validated against the data. Once we validate our method, we can use simulated dataset to supplement available observations in PFDA model development. To validate the simulated fault displacement from our dynamic rupture models, we choose the 1992 Landers earthquake fault validation exercise. Because Landers is the third largest California event in the 20th century and has high quality and a good complete data sets of fault displacement and ground motions. Particularly for fault displacement, this event has diverse measurements. One style is traditional field geological survey mapping, and another style is contemporarily detected mapping from satellite. In the traditional field observation, the fault offset is like the left panel and a rapid change of the deformation across the fault plane. That is to say, the fault offset occurs along the line. But with the help of contemporary satellite imaging in the landers, the fault displacement is like the red pattern of partially distributed deformation. The overall deformation consists of discrete offset, as we see in the field, and the stretching deformation within a narrow zone near the fault trace caused by the inelasticity of host rock. As a matter of fact, the distributed off-fault deformation pattern is systematically observed by the satellite in landers. The off-fault distributed deformation is occurred within a narrow zone of few tens to 100 meters to the fault trace. The total deformation across fault trees is called total displacement. The total displacement accommodates the on-fault offset that is measured in the field reconnaissance, and the rest of the deformation is distributed off the fault. It's called off-fault displacement, or OFD. In landers, the OFD on average accounts for almost 50% of the total displacement. That is to say, the missed fault displacement is comparable to the measured on-fault displacement. In this sense, if we only consider the on-fault or field surveyed displacement in puffed model development, the fault displacement hazard might be underestimated. To generate the physics-based fault displacement, particularly the missed alpha part, we initiate our dynamic rupture model. To be useful in informing puffed modeling, our model is not aimed to reproduce all details of Lander's earthquake, but makes it general enough to capture the key features of fault displacement. Thus, it makes our model more generic and extendable. This is how we set up our model. In the middle, the light green curves are the pre-rupture mapping that is prepared for the Alquist per Euler earthquake zoning. We treat it as the prior information we know about future earthquakes. Red curves are the surface rupture of landers. We see they are spatially correlated. For better quantifying the future hazard in the tractable manner, we simplify the fault geometry in this region as a three-segmented fault plane as the thick black line. On top of three-segmented fault, we add geometrical roughness to capture modeling uncertainty and add a long strike variability. Thus, we can see the shear and the normal stress are both perturbated by the geometrical roughness. In terms of the rock material, we adopt 1D Mojave velocity structure that is adopted from the SCAC-B BP module. Tectonic stress is derived or inferred from previous stress field model. The applied stress has three different orientations depending on the location as blue arrows. Finally, we adopt the Hunk-Brown plasticity model to mimic the off-fault inelastic deformation. Here are our simulation results. We managed to simulate the similar partially distributed deformation pattern observed in Lander's earthquake. Then we follow the procedure down over the aerially detected deformation to pick the total and on-fault displacements and make them two diverse measurements over our simulation results. Then we compare the simulated on-fault and the total displacement with Lander's dataset. Especially, we find the simulated total displacement is in agreement with the observed cumulative displacements, and our model generally reproduces the amplitude and the location of the peak displacement. The intermediate to large-scale statistical characteristics of both on-fault displacement and total fault displacement are also consistent with observations. Then we statistically compare the simulation with data. Left figure shows the correlation of on-fault displacement and total displacement in simulation and observation datasets. Both show the very similar tendency that the total displacement is larger than on-fault displacement because the slope is larger than 1. Besides, the best fitting slopes between the total and on-fault displacement in simulation and the data are very similar. This slope is very important because it may help to quantify the unknown total displacement in some Asian earthquakes without knowing the area measurements or the information about the total displacements. OFD ratio is the ratio between the off-fault deformation and the total fault displacement, implying how much displacement or deformation is accommodated in the all-fault regime. Uh, Both observation and the simulation showed OFD ratio follow a nearly normal distribution, and the mean value of OFD ratio are very close. 42% for simulation and 46% for observations. Our simulation also models the ground motion, even though it is a byproduct. We perform a sanity check for validating the physics important to ground motion is also properly modeled. Red curve shows the mean bias of dynamic rupture relative to data from 1 to 10 seconds. The gray shaded area is the range of 4 GMP median predictions. Relative to GMP, our model well addressed the event term of unilateral rupture. In general, our dynamic rupture model captured the ground motion in periods lower than 5 seconds. Longer period misfit may be caused by the 3D velocity structures. To capture the modeling uncertainty, we relax some input parameters like tectonic stress level, fault roughness, but we remain the rest of parameters are identical. We create a suite of dynamic rupture models and use resultant magnitudes to generate the mean average of fault displacement datasets. As similar shown in the earlier model, the location of the peak displacement is well consistent with Langer's earthquake. It implies that the information of fault orientations and stress orientations are important to fault displacement. Here we make a magnitude matched test. We pretend not to know the right magnitude of Langer's, given our simulated templates of the fault displacement, comparing the displacement amplitude and the gradient, which magnitude being average curves is your preference to match the Langer's data. I'll shoot 7.2 to 7.4 between two curves that cover the ground truth of the Langer's, 7.3. The scaling relationship between average displacement and magnitude is often used by PSHA and PFDHA PFDM models. Our own fault displacement datasets were close to previous empirical datasets and developed the scaling law. There are 4 new data points for Langer's, Hector Mai, Darfield, and Balochistan, showing the aerially detected displacements or total displacements or systematically larger. Our simulated total displacements are closer to these 4 datasets relative to the empirical datasets. Using the empirical datasets or on-fault displacement missing off-fault part may be under-predict the fault displacement hazard, but the new observation of error-detected measurements are too few to support perfect model development. Therefore, a validated dynamic rupture models like the one used in Langer's scenario has a potential opportunity to supplement the observations and reliably quantify the fault displacement hazard. And in this slide, we will show our prospective directions of physics-based fault displacement simulations. We will extend our application to a non-event specific scenario. In this study, we target Langer's earthquake, but in the future, we will target a more generic strike-slip fault. And then we'll expand the simulated magnitude from magnitude 5 to magnitude 8. This will help us to validate the simulated fault displacement varying with different magnitude against the whole set of FDHI datasets. Here is our current progress of this effort. We'll make a example of strike-slip simulation from magnitude 5 to magnitude 8. It explores both on-fault displacement, gray dotted, and total displacement, gray crosses. As shown in this figure, the mean magnitude trend of the maximum displacement for both on-fault green lines and the total displacement black lines, they show a great agreement with FDHI datasets. Next, we plan to extend this methodology to diverse fault types like reverse or normal faults. In addition to Lander's validation, we'll plan more event validation like Ridgecrest or Chi-Chi or other candidates that have very good documentation of fault displacement data. Okay, a take-home message and paper. This study shows dynamic rupture model is a viable and powerful approach to address the fault displacement hazard. And the dynamic rupture model has the capability of simulating total displacement, alpha deformation ratio, and their correlations that are all consistent with those observed in Lander's earthquake. Um, and our model can also simulate ground motions that are comparable to observed level of ground motion within a reasonable uncertainty. So in summary, dynamic rupture model is considered as an effective model to serve both hazard analysis of fault displacement and ground shaking. And our study about Lander's validation have been published in a BSS special issue. If you are interested to know more details about this work, here is the link for this paper. Thank you very much for listening. Any questions?